In this lecture, we look at sound waves. Sound waves are oscillations in pressure and displacement of the medium. For example, let's look at a pressure pulse traveling down a tube. Here we have an actuator or piston that pushes into the tube, creating a denser region of air, then propagates down the tube. Let's look at this in more detail. We'll just take a single chain of air molecules and look at what happens when a pulse travels down this chain. We mark a red molecule which comes in from the left and strikes the first blue molecule, which then strikes the next one, and so on. So that what we see is that the displacement of any single molecule is small, because soon after it starts to move, it collides with the next molecule and stops. So the displacement of air molecules is small, but the pulse travels down the whole chain at a fairly fast speed. And what is the speed of this disturbance? Well, it's given by this velocity is equal to the square root of the elastic property of the medium divided by the inertial property of the medium. For the speed of sound, this is equal to the square root of b. B is the bulk modulus, or how hard it is to compress or stretch the medium, or in other words, this is the elastic property for sound. And rho is the density of the medium. Here we have a few different media and the speed of sound related to in these media. Cold air has a speed of sound of 331 meters per second. If you warm the air up a bit to room temperature, 20 degrees, the density goes down a bit and the speed of sound goes up to 343 meters per second. Hydrogen is even less dense. It's a very light gas. Its speed of sound is 1,284 meters per second. Water is even more dense than any of the gases. However, it is also very hard to compress or stretch water. So its speed of sound is equal to 1,482 meters per second because its speed is very large, even though its density is also larger than air or hydrogen. Steel is even harder to compress, so that its speed of sound ends up being 5,960 meters per second, even though it is also very dense. Let's look at an example. Let's look at aluminum. The bulk modulus of aluminum is equal to 76 times 10 to the 9th newtons per meter squared, and its density is 2,700 kilograms per meter cubed. So what is the speed of sound in aluminum? Well, we can use our formula, taking the square root of b divided by the square root of rho. That's the square root of 76 times 10 to the 9th newtons per meter squared divided by the square root of 2,700 kilograms per meter cubed. And that gives us 5,300 meters per second. If you are designing an ultrasonic device to look for defects in a piece of aluminum, for example, an airplane's wing, what frequency would you need to detect a defect that is 100 times 10 to the minus 6 meters in size? That is the size of a human hair. Assume you will need a wavelength on the order of the size of the defect. V sound is equal to lambda times f. That's true for any wave. So that then if we rearrange this, the velocity of sound divided by the wavelength is equal to the frequency. So that then the frequency then is 5,300 meters per second divided by the wavelength we desire, 100 times 10 to the minus 6 meters. And that gives us 53 megahertz. So a high frequency in the radio frequency range.